Rings Introduction. Dear learners, today we are going to learn about rings. Let's start with the ring introduction. In mathematics, a ring is an algebraic structure consisting of a set together with two binary operations usually called addition and multiplication, where the set is an abelian group under addition called the additive group of the ring and a monoid under multiplication such that multiplication distributes over addition. In other words, the ring axioms require that addition is commutative, addition and multiplication are associative, multiplication distributes over addition, each element in the set has an additive inverse and there exists an additive identity. One of the most common examples of a ring is the set of integers endowed with its natural operations of addition and multiplication. The branch of mathematics that studies rings is known as ring theory. Ring theory may be used to understand fundamental physical laws such as those underlying special relativity and symmetry phenomena in molecular chemistry. The concept of the ring first arose from attempts to prove Fermat's law theorem, starting with Richard Dedekind in the 1880s. After contributions from other fields, mainly number theory, the ring notion was generalized and firmly established during the 1920s by M.E. Noether and Wolfgang Grull. Let's nail down the definition of ring. Definition of ring. A ring is a set R together with two binary operations addition and multiplication denoted plus and dot respectively, which satisfy the following axioms. Firstly, R is an abelian group under addition with 0 as the identity. Closure. For all a comma b in R, we have a plus b in R. Associativity. For all a, b and c in R, we have a plus b plus c equal to a plus b plus c. Identity. There is an element 0 belongs to R such that for all a in R, a plus 0 equal to 0 plus a equal to a. Inverse. For all a in R, there exists b belongs to R such that a plus b equal to b plus a equal to 0. B will be denoted as minus a. Commutativity. For all a and b in R, we have a plus b equal to b plus a. Next, multiplication is closure and associative. Closure. For all a comma b in R, we have a b in R. Associativity. For all a, b and c in R, we have a dot b dot c equal to a dot b dot c. Finally, we require that addition and multiplication are compatible in an obvious sense. Distributivity. For all a, b and c in R, we have a dot b plus c equal to a dot b plus a dot c. B plus c dot a equal to b dot a plus c dot a. Next is definition of ring with unity. If E be an element of a ring R such that E dot a equal to a dot e equal to a for all a in R, then the ring is called the ring with unity and the elements E is said to be unit element or unity or identity of R. Let us see some examples of rings. Consider the set of integers is set with the operation usual addition plus and multiplication dot. Let us check ring properties. In previous module, we have already seen that Z comma plus is an abelian group. So far, now it is enough to check the properties for multiplication only. Let us verify it. Closure. for all a comma b in Z, clearly AB is also in Z. Associativity, for all A, B and C in Z, we have A dot B dot C equal to A dot B dot C. Distributivity, for all A, B and C in Z, then following holds. A dot B plus C equal to A dot B plus A dot C and B plus C dot A equal to B dot A plus C dot A. Thus, the set of integers is said with the operation usual addition plus and multiplication dot forms a ring. Also note that an element 1 belongs to Z, then clearly 1 into A equal to A and A into 1 equal to A for all A belongs to Z. Therefore, Z comma plus comma dot is a ring with unity. Next example is, consider the set of all complex numbers C under complex addition plus and multiplication dot. Let's check ring properties. In previous module, we proved C comma plus is an abelian group. So, let's check the properties for multiplication only. Closure, clearly product of two non-zero complex numbers is again a non-zero complex number. Associativity, clearly Z1 into Z2 into Z3 equal to Z1 into Z2 into Z3 for all complex numbers Z1, Z2, Z3 belongs to C. Distributivity, let Z1 equal to A1 plus IB1, Z2 equal to A2 plus IB2 and Z3 equal to A3 plus IB3. Then to show that Z1 dot Z2 plus Z3 equal to Z1 dot Z2 plus Z1 dot Z3 and Z2 plus Z3 dot Z1 equal to Z2 dot Z1 plus Z3 dot Z1. Thus, the set of integers C with complex addition plus and multiplication dot forms a ring. Also, the identity element 1 equal to 1 plus I into 0 belongs to C and 1 into Z equal to Z into 1 equal to Z for all Z belongs to C. Therefore, C comma plus comma dot is a ring with unity. Let us verify real numbers with usual addition and multiplication in the next example. Consider the set of real numbers with the operation usual addition and multiplication. Let us check the ring properties. In previous module, we proved real numbers under usual addition is abelian group. Next, we verify the closure property. Let A comma B belongs to R. Then clearly the product of two real numbers is also a real number and so AB belongs to R. Associativity, clearly A dot B dot C equal to A dot B dot C for all A, B, C belongs to R. Distributivity, let A, B, C belongs to R. Then clearly A dot B plus C equal to A dot B plus A dot C and B plus C dot A equal to B dot A plus C dot A. From the above discussion, all the ring properties holds in real numbers under usual addition and multiplication, and so the real numbers under usual addition and multiplication is a ring. Since an element 1 belongs to R, we have 1 into A equal to A and A into 1 equal to A for all A belongs to R. Therefore, the real numbers under usual addition and multiplication is a ring with unity. The next example is, let R equal to set of all A plus B root 2 such that A comma B belongs to Z. Then we are going to show that the set R is a ring. Clearly, R is an abelian group under usual addition. Let A plus B root 2 and C plus D root 2 are in R. Then A plus B root 2 into C plus D root 2 equal to AC plus 2BD plus BC plus AD into root 2 are in R. Since the two binary operations are the usual addition and multiplication, the distributive laws and associative law hold. Thus, R is a ring with usual addition and multiplication. The next example is, the Gaussian integers are the subset of the complex numbers consisting of all complex numbers C with integer coefficients A plus IB such that A comma B belongs to Z. We write them as Z of I. Then clearly, Gaussian integers forms a ring under complex addition and multiplication. Example, consider the set R equal to Zn under addition modulo and multiplication modulo n. Now, we are going to show that the set R is a ring. In the previous module, we proved Zn comma plus circle is an abelian group under multiplication modulo is an associative binary operation. We now prove that the distributive laws. Let A, B, C belongs to Zn. Then B plus circle C is congruent to B plus C mod n. Hence, A dot circle B plus circle C is congruent to A into B plus C mod n. Also, A dot circle B is congruent to AB mod n and A dot circle C is congruent to AC mod n. So that A dot circle B plus circle A dot circle C is congruent to AB plus AC mod n. Since A dot circle B plus circle C and A dot circle B plus circle A dot circle C are in Zn, we have A dot circle B plus circle C is equal to A dot circle B plus circle A dot circle C. Similarly, A plus circle B dot circle C is equal to A dot circle C plus circle B dot circle C. Therefore, distributive laws hold. Hence, Zn plus circle dot circle is a ring. Example, consider the set R equal to rho of x delta intersection. Then we are going to show that the set R is a ring. In the previous module, already we have seen rho of x delta is an abelian group. Also, intersection is an associative binary operation on rho of x. Also, it can be easily verified that A intersection B delta C equal to A intersection B delta A intersection C. A delta B intersection C equal to A intersection C delta B intersection C. Hence, R is a ring. Next example is, let R be the set of all real functions. We define addition and multiplication by f plus g of x equal to f of x plus g of x and f g of x equal to f of x into g of x. Then we are going to show that the set R is a ring. Clearly, addition and multiplication is associative and commutative. The constant function 0 defined by f of x equal to 0 for all x belongs to R is a 0 element of R and minus f is the additive inverse of f. Hence, R is an abelian group. The associativity of multiplication and the distributive laws are consequences of the corresponding properties in R. Hence, R is a ring. The next example is, let A be any abelian group and homomorphism of A be the set of all endomorphisms of A. Consider f comma g belongs to home of A. We define f plus g by f plus g of x equal to f of x plus g of x and f g equal to f composition g. Then clearly home of A is a ring. Next example is, consider the set S equal to set of all A by 2 power r such that A comma r belongs to Z and r greater than or equal to 0. Then we are going to prove that S is a ring. Clearly 0 equal to 0 by 2 power 0 and 1 equal to 1 by 2 power 0 are in S. Suppose alpha and beta are elements of S. We can write alpha equal to A by 2 power r and beta equal to B by 2 power S, where A, B, R and S belongs to Z and R and S are greater than or equal to 0. We now to check that alpha plus beta minus alpha and alpha beta are in S. Note that minus alpha equal to minus A by 2 power r and alpha beta equal to AB by 2 power r plus S. Clearly minus alpha, alpha beta are in S since A plus B, R plus S are integers and R plus S are greater than or equal to 0. Now for the sum, we will assume that without loss of generality r greater than or equal to S. Then alpha plus beta equal to A plus 2 power r minus S into B by 2 power r. Now since A, B, R and S are integers and r greater than or equal to S, we have A plus 2 power r minus S into B is also an integer. Clearly alpha plus beta is in S. Since associative and distributive laws are held in S, therefore S forms a ring. Next, let us see some types of rings. The first one is null ring. The singleton set 0 with binary operation plus and defined by 0 plus 0 equal to 0 and 0 dot 0 equal to 0 is a ring called the 0 ring or null ring. The second one is commutative ring. If the multiplication in a ring is also commutative, then the ring is known as commutative ring. That is, the ring R with addition and multiplication is a commutative ring provided. A dot B equal to B dot A for all A comma B belongs to R. If the multiplication is not commutative, it is called non-commutative ring. Third one is ring with unity. If E is an element of a ring R such that E dot A equal to A dot E equal to A for all A belongs to R, then the ring is called the ring with unity and the elements E is said to be unity or identity of R. Fourth one is ring with 0 divisors. A ring R comma plus comma dot is said to be a 0 divisor of 0 or 0 divisor if any A belongs to R, there exists a non-zero element B belongs to R such that A dot B equal to 0 or B dot A equal to 0, where 0 is the additive identity in R. Here A and B are called the divisor of 0. Fifth one is ring without 0 divisor. A ring R is said to be without 0 divisor if the product of no two non-zero elements of R is 0. That is, if AB equal to 0, then we have A equal to 0 or B equal to 0. Next, let us see that some basic properties of rings. The first property is, let R be a ring and let A and B be elements of R. Then first one is 0 dot A equal to A dot 0 equal to 0. Second one is minus A into B equal to A into minus B equal to minus of AB. Third one is minus A into minus B equal to AB. Fourth one is A into B minus C equal to AB minus AC and B minus C into A equal to BA minus CA. Furthermore, if R has a unit element 1, then the following holds. Minus 1 into A equal to minus A and minus 1 into minus 1 equal to 1. Second property is, let R be a ring with identity E. Let A belongs to R, and suppose that x and y are multiplicative inverse of A, then x equal to y. The third property is, let R be a ring and let A and B be any two elements of R. Then A plus B the whole square equal to A square plus AB plus BA plus B square. Fourth property is, let A and B be two rings in A cross B. We define A1 comma B1 plus circle A2 comma B2 equal to A1 plus A2 plus B1 plus B2 and A1 comma B1 dot circle A2 comma B2 equal to A1 A2 comma B1 B2. Then A cross B is a ring. This ring is called the direct sum of the rings A and B. It is denoted by A plus circle B. Fifth property is, let R be a ring. We say that R is unitary ring if E belongs to R is such that AE equal to EA equal to A. For all A belongs to R, then E is called a unity for the ring. Sixth property is, let R be a ring. We say that R is a Boolean ring if for every A belongs to R, A square equal to A. For example, let X be any set and row of X be the set of all finite subsets of X. Then row of X comma delta comma intersection is a Boolean ring. Seventh property is, let R comma plus comma dot and S comma plus comma dot be two rings. A bijection F from R to S is called an isomorphism if F of A plus B equal to F of A plus F of B and F of AB equal to F of A into F of B for all A comma B are in R. Okay learners, now we come to the conclusion part. Up to now we had seen about rings. First we had seen that the concept of rings starts in 80s and it is established during 1920s. Then we had seen the proper definition of it. By using the definition, we had proved set of all integers and set of all real numbers with the usual addition and multiplication forms a ring, and set of complex numbers with the complex addition and multiplication forms a ring. Further, set of all integer modulo n with modulo addition and modulo multiplication forms a ring. Moreover, we had seen some types of rings like null ring, commutative ring, etc. Finally, we had finished this session by discussing about some properties of the ring. I hope you get the basic concepts of ring. The upcoming sessions will give more details of ring structure briefly. So, we will meet in the upcoming sessions. Thank you.